Okay, hello everyone, and welcome to another session of this course. Can you just write in the chat if you can hear me? I just want to make sure that my sound is correct. Okay, great. So let me start by sharing my screen and continuing where we left off in the previous session. Okay. So last time we talked about the whole system of our blockchain and our protocol from the point of view of a normal node. And the idea here was that as a normal node, you have to perform several different actions in this protocol. You have to make connections to other nodes, you have to propagate transactions, and you have to propagate blocks. And of course, you have to keep track of your own blockchain, and if you like, your own mempool, and you have to validate the transactions and the blocks, as we talked about in detail in the previous session. But today I'm going to mostly focus on how the system looks like from the point of view of a miner. So what happens if you are a user who wants to actually add new blocks? And just one point that I want to emphasize again and again is that there is nothing in the protocol that limits who can be a miner. So anyone who connects to the network can decide to be a miner. And this whole distinction between a normal node and a miner is just something that we are making for academic reasons. And the idea is that I call someone a normal node if they don't want to take part in the mining and creating of the new blocks. Okay, so now let's talk about the point of view of a miner. And again, remember that a miner is basically any node who takes part in creating new blocks. And of course, in our current system, this means that the miner takes part in doing proof of work and solving the hash cache puzzle that we talked about. Okay, so one important point here is that the miner does everything that a normal node does. So it's not like when you're a miner, you stop doing the normal things. So the first thing a miner does is that basically everything a normal node does. Okay. But here's the problem. Suppose that you are a miner. So of course, we're going to talk about how you're going to do your mining and so on. But one important point other than that is that you really need to be connected very well to the network. Because remember that when we were talking about normal nodes, there was this idea when propagating transactions that if you see two transactions that are double spending the same amount of money, the same coin, you will put one of them as valid and one of them as invalid, right? And you only propagate the ones that are valid. So again, going back to this famous figure that we had here. So suppose that I have a transaction that gives 5 Bitcoins to Alice, and then Alice is spending this 5 Bitcoins twice. Once she's spending it to send to Bob and once to Carol. Now, as a normal node on the blockchain, when you get these two transactions, you don't really care which one should be considered valid and which one invalid. So most of the nodes will just say, okay, the first one I received, I assume is valid, and the second one I will assume is double spending, and I will not propagate the second one. But suppose that you are a miner. So as a miner, you're in charge of creating the blocks. And of course, as we talked about before, you're going to be paid some money for creating these new blocks. And it came in two forms. There was the block reward, and there was also the transaction fees. So it might be that as a miner, you really prefer the second transaction. Maybe the first transaction gives you, let's say, I don't know, 1 unit in transaction fees, but the second one gives you 100 units in transaction fees. So as a miner, you might prefer to know about the second transaction, and you might prefer to include the second transaction in your block. But the problem is that if you just connect to the network like any other normal node, you might not even hear about this second, more lucrative transaction. It might be that you're connected to a part of network that only knows about transaction 1 and discards transaction 2, okay? So, and we will get into more details on this, but for now, the main difference that we have for a miner node is that generally we should have a better connection to the network. And what this means is that every miner actually creates several different nodes and connects, puts them in different geographical locations. Maybe they have one node in Asia, one in Americas, one in Europe, and then they try to connect to different parts of the network so that they can hear about all the activity and all the transactions that are happening. So the first thing here about miners is that you need better connectivity. And as I said before, this is achieved by deploying several nodes instead of just one. Okay, but now let's actually get into the things that the miners do and others do not do according to the Bitcoin protocol. So, of course, one task that you have is forming blocks. Okay. So what does this mean? Well, everyone listens for transactions on the network, and the miners are just like that as well. So as a miner, you hear a lot of transactions. And as I talked before, since a miner does everything that a normal node does, the miner is keeping track of the blockchain. So let's say this is the blockchain that you have as a miner. So this is a chain of blocks. And let's say that you also have a mempool of transactions. Oh, sorry. Okay. So now you want to form a new block. And we talked about what goes into a block, right? So I will have this block B, and it was supposed to have several things. So it has the Merkle root of all the transactions. Maybe this is a bit small, okay. Merkle root of the transactions that goes into it. It will also have a nonce, as we talked about before. And it will have the public key or address of the miner. It will have a hash pointer to the previous block. And additionally, it will also have a timestamp that is set by the miner. So one point that I actually wanted to really emphasize here, because it's also useful in the homeworks, is that both transactions and blocks actually do have timestamps on them. But these timestamps are not trustworthy. So whoever creates the transaction or whoever creates the block also puts in the timestamps. Okay. So this is what our block usually consists of. And in Bitcoin, we will have a bunch of other things. And in some other blockchains, we will have some extra metadata as well. But I'm not going to consider that right now. The problem is that what happens when you form a block? Well, the idea is that you want to form this block, and then you want to solve the proof of work puzzle. And then if you solved it correctly, you want to publish this block. So one of the first problems that happens here is that this block that you are creating cannot have infinite size. Because it is true that at the end of the day, the only thing that goes on the blockchain is this block header, basically, the Merkle root, the nonce, and so on, and this has a fixed size. right? So if you think about it in terms of how much space it takes, this has a fixed size, right? But the problem that we have is that, well, every other node should be able to verify the validity of this block. And as we talked about in the last session, the validity means that every transaction in the block also has to be valid. So even though only the block ends up being in the blockchain, we actually have to propagate the whole Merkle tree. And of course, that's a lot of communication that we're going to be doing. So we want to limit the size. We don't want to have blocks of infinite size, basically. And of course, that's also important because we don't want to have too much delay in our network, and we want everyone to be able to hear about every block after a while. So it's rational to put a limit on the size of the block. And when I say on the size of the block, I don't mean just these header things, but I actually mean on the total size of the Merkle tree and the header, all of it together. So this is one of the things that exists in Bitcoin. So there is a cap on block size. And what that means is the size of the block header, or in this case, I'm calling B, plus the size of the tree of transactions, which we call the T, the Merkle tree. So here, of course, we have the Merkle root of T. Okay. So something is wrong with my Zoom. Okay. So what is the limit in Bitcoin? Well, actually, the Bitcoin limit is 1 million bytes. And so 10 to the power of 6 bytes. So what this means is that whenever you create a new block of transactions and you want to propagate it to the network, you want to send it to the network, the size of the block that you have created, the overall size of the thing that has to be propagated should be at most 1 million bytes. Okay. And I have to say that other currencies have different block sizes. Especially there are many variants of Bitcoin that have increased this block size sometimes to several gigabytes. But what matters the most is that there is some limit that is set in the protocol. And in case of Bitcoin, it's 10 to the 6 bytes. Okay, but this immediately creates a problem for us as a miner. Since there is a limit on the size of the block, that means that I cannot put any transaction that I see into that block. Right? So I have 10 to the power of 6 bytes, and I have seen a lot of transactions. I have to choose which transactions I put into my block. So forming the block is actually kind of a hard algorithmic problem. So the algorithmic problem that we have here is what? It's that given a bunch of transactions, so given a set of transactions that are basically the transactions that my different nodes have seen all around the world. Actually, let me give the set of transactions a name. Given a set S of transactions, choose a subset of S with total size at most this much. So since this is the maximum block size, let's just give it a name. Let's call it M because it's the maximum size. So the problem that we have to solve is that we have to choose a bunch of transactions such that their total size is at most m. And also, of course, we want to create a valid block, right? So the other problem that we have is that we want to make sure that there is no double spending. So given a set S of transactions, choose a subset of S with total size m that has no double spending. And now when I say no double spending, what do I mean? Well, I first mean no double spending with respect to the current blockchain. Because of course, if I have a transaction in my block that is double spending something that was already on the blockchain, that's going to be rejected. And I shouldn't also have double spending with respect to my own block, right? So I cannot have two transactions in my block as a miner that both spend the same coin. That's not acceptable. So this is what I want to do. And of course, this is not such a hard problem if you look at it just the way it is. I have a set of transactions. I want to choose a subset, and I want to make sure there is no double spending. So I can do it greedily, right? So I can start from the beginning of my set, from the first transaction in my mempool or my mempools, if I have several nodes. And I can just check if this transaction has no double spending, and if I have enough room for it, I will put it into my block. Then I choose the next transaction and so on. I just continue. And whenever I see a transaction that is too large and doesn't fit into my block, I don't put it in. Or whenever I see a transaction that has done some double spending, I will not put that in either. Okay. So in its current form, solving this algorithmic problem is not a big deal, but we will come back to it and we will see how it will get harder later on. Okay. So this is the first step. So I'm forming a block. Actually, let me write it like this. Let's say forming a block B. Now, the next step is, of course, solving the proof of work, right? So the next step is solve the proof of work puzzle. So what does this mean? I have my block, and of course, I didn't put anything for the nonce. And the idea was that I have to find a nonce such that the hash of my block becomes really small, right? And so this is the thing, find a nonce such that the hash of the block becomes small. Okay, now let's go into the details of this and how we will do it. So the first thing is that what is this hash function exactly? And this also depends on your cryptocurrency. In Bitcoin, the hash function, as I said before, is just 2 iterations of SHA-256. So in Bitcoin, okay, actually, let me use a different color. In Bitcoin, this H is basically just the SHA-256 hash function applied twice. Okay. So that's the first problem. The second problem is, what do we mean by it becomes small, right? So if I apply the SHA-256, remember that one of the main properties, it was actually the definition of a hash function, is that it gets inputs of any size, but it gives me an output of a fixed size. And in case of SHA-256, I have an output with 256 bits. So I have 2 to the power of 256 different possible outputs. And when I say it becomes small, I mean the output becomes less than some predefined threshold, right? So let me create a new slide here. And we're going to progressively make this more specific. So I would say find a nonce such that the hash of V becomes less than or equal to some threshold D, which is called the difficulty of mining. So we call this difficulty or threshold of mining. And again, one of the things that a lot of you asked before and also in emails to me is, how is this D set? And here's how we set D. So here's how the protocol talks about D. So in Bitcoin, what happens is that D is reset every 2016 blocks, if I'm not wrong. Hopefully I got the number right. Okay. So what does this mean? This means that whenever you have a block in your blockchain whose number is divisible by 2016, at that point, you know that your difficulty is going to be reset. Okay, but how do we reset the difficulty? We just look at the timestamps of all the previous blocks from the previous reset until now. So just the idea is that look at the timestamps of blocks from the previous reset until now. And by the way, one point here is that 2016 blocks is almost, I think, a week or maybe 2 weeks of time. Yeah, I'm not going to do the calculation. Anyway, each block comes in 10 minutes. So this is 20,160 minutes almost. Okay, so we look at the timestamps of the previous, from the previous reset until now, and we just figure out if the amount of time that has passed is less than or more than 2016 times 10, okay? And what's our goal? Our goal is to make sure that on average, one block is found every 10 minutes. And if I look at the timestamp of the block that did the previous reset, and I look at the timestamp of the block that is doing the current reset, I can just subtract them and see if the amount of time that has passed was more than 20,160 minutes or less than that. And then there is a formula that is hard-coded in the Bitcoin protocol, and based on that formula, I will reset the value of D. Okay? And that formula makes it harder to do mining if the mining has taken less time than expected, and it makes it easier if the mining has taken more time than expected. Okay, but the important point here is that since this resetting is basically based on the blocks that are already on the blockchain and based on the timestamps of these blocks, everyone is in consensus about the value of D and how it is reset, right? So remember that the thing that everyone has consensus about is the blockchain. And this D is now basically a function of this blockchain that everyone has consensus about. So everyone knows exactly what the value of D is. Okay. So going back to this, actually, maybe I can show you a few nice charts here. Let me just change. Just a second. Okay. Okay, so if you look here, actually blockchain.com gives us all this information and the historical variants of them, and you can find it at this URL. So there are some things that can tell you, for example, what was the block difficulty in different points of time. And as you see here, every now and then the difficulty is suddenly reset. Okay, so sometimes the difficulty goes down, sometimes it goes up. It depends on how much it took for the previous 2016, yes, 2016 blocks, which is almost 2 weeks to be mined. So if the previous 2016 blocks took, let's say, 3 weeks to be mined, then we will increase the difficulty a lot so that we make sure that the next 2016 blocks take approximately 2 weeks. Otherwise, we will decrease the difficulty. Okay, and actually there are some other things here as well that we can talk about. So the difficulty, if you think about it, really depends on the hash rate of the whole network. So what are these miners doing? Let me go back to my other share. I really don't like Zoom, but there's no way other than this. Okay. So when I say find a nonce, what do I mean here? As a miner, how do we find a nonce? Well, the idea was that when I say find a nonce, I do it just by randomly trying possible nonces. Okay, so this just means try random nonces and compute hashes. So compute hash of B over and over again until this hash is small. Okay, until hash of B is less than D, less than or equal to D. Okay, this is what I mean by finding a nonce. So in a sense, if everyone is using this algorithm, if every miner is using this algorithm, whether we can find this hash or not, whether we can find a nonce that makes this hash small enough or not, really depends on how many hashes we can compute in every second, right? So think of this hash function as some sort of a random function. We don't really have a proof that it's random, but let's say it gives us a random distribution over all the possible outputs. If it's truly random, then what happens is that in order to get the hash to be less than or equal to D, how many different hashes should I compute? Well, if I just choose a random nonce, let's do it like this, with a random nonce, I would say that the probability that my hash is less than or equal to D is, well, if I want it to be less than or equal to D, then I have D plus 1 choices, right? So my output should either be 0 or 1 or 2 or all the way until D. So that's D plus 1 divided by what are the number of possible hash outputs that I can have? Well, it's 2 to the power of 256. Okay. So based on the difficulty, this is the probability that you get it right if you do if you just check one random nonce. Okay. And of course, this is not a really good analysis. This is a naive analysis based on assuming that the hash function is somehow random. It's not really random in the real world. But anyway, the point that I'm trying to make here is that if the difficulty is, if this D is small, if the hash puzzle is really difficult, then this probability is really small. So in order to solve it and be able to add a new block, you have to do this many, many times, right? Okay, so there is a question that asks, can you explain why it is D plus 1? Well, you see the output of my hash function has 256 bits. So I have 2 to the power of 256 different possible outputs. And which one of these outputs are acceptable? Only the ones that are smaller than or equal to D. So from 0 to D, and there are D plus 1 numbers from 0 to D. So I have D plus 1 acceptable outputs out of a total of 2 to the power of 256. So the number of acceptable outputs is really small. And again, assuming that this hash function is random and it's also giving us the uniform distribution, which are really strong assumptions and might not hold in the real world, then this is the probability that we get it right. Or in other words, what that means is that I expect to be able to find a nonce. So as a miner, I expect to find a valid block or a valid nonce for a block after trying almost 2 to the power of 256 divided by D plus 1 different nonces. Okay, let's call it random. So this is your chance of finding a new block. And actually this chance is really, really small. This probability is really, really small, which means that as a real world miner, if you're doing it, for example, let's say on your computer, the chances of you finding any valid blocks in your whole lifetime is almost 0. Okay. So we have a question that has, is it true that the probability of SHA-256 is equally the same for each output? No, we're just assuming that for now, just to do a naive analysis. I will come back and talk about that probably either in this session or next session. There is some extra assumption that we have on our hash functions, and this was what I skipped over when I was talking about hash functions, the puzzle friendliness. And I will at some point talk about puzzle friendliness. But for now, just let's assume that it's random, even though it's not in the real world, so that we can do this naive analysis. Okay. So actually, in this case, I don't really care about the +1 because anyway, I'm doing an approximation. So this is how many different tries I have to do. So if this D is small, which it is in the real world, and what I mean by small is, I mean, even if it's, let's say, 2 to the power of 230, that's still a lot of hashes that you have to compute. In the real world, it's much smaller than that. Okay, so what does this mean? This means that if we have the D, if we know the difficulty or the threshold that we need for mining, and if we look at the network and see how often a new block is created, we can kind of approximate how many hashes are being computed, right? And we can also approximate how many hashes are being computed every second. Because we know approximately how many hash computations it takes to find a new valid block. And as an observer in the network or as a node on the network, I can see when new blocks are arriving. So every time a new block arrives, I can look at its hash and I can see, okay, how many tries did it take approximately to find this hash? And based on that, I can approximate the total hash rate of the network or the total number of hashes that the Bitcoin network or any other currency like this can compute in a second. So let me again change my sharing and show you this data because it's truly amazing. So, okay, now here on blockchain.com, I can just go to total hash rate. So this is the total hash rate of the Bitcoin blockchain, which means, and the unit is terahashes per second. So the idea is how many terahashes can the network compute in every single second. And as you see here, it goes up and down, but generally the trend is upwards. And right now it's around 200 million terahashes per second. It's such a large number. It's really weird. Okay. And of course, there's a lot of talk that, well, computing these many hashes takes a lot of energy, does a lot of damage to the climate and so on, and all of these are true. So Bitcoin is one of the major polluters right now in terms of the energy that it consumes. And of course, this energy only goes into mining the blocks and computing these hashes over and over again. So a lot of people actually call it just waste, because to be honest, just computing hashes over and over again doesn't really have any real world application other than securing the blockchain. And that's not something that people really like. Okay, but let me go back to the point of view of the miners, because I want to stick to computer science mostly and not talk so much about the other aspects of it. Okay, so back here, you're a miner, so you first form a block B. And after you form your block, you will continue and compute hashes, compute nonces, and then hashes with those nonces over and over again until you find a nonce that matches your difficulty threshold. Okay, so, but what happens after you found a nonce? So after you find a nonce, of course, you have to broadcast the block that has the right nonce, and also the Merkle tree of all the transactions to the whole network. So the next step after finding a valid nonce is to broadcast the block B and of course all of the transactions in that block, so the Merkle tree T, to everyone in the network. And of course, the way that you do this is very similar to how you announce a new transaction. So you use your node or all of your nodes to just send this to your neighbors, and then they will send it to their neighbors and so on, and it will be broadcast on the internet. Okay. Something is wrong with the sharing, so I'll try again. Okay, is it working now? Okay, great. Sorry about that. So after you find a valid nonce, you just broadcast your block, which now has this valid nonce, and everyone can check that it has a valid nonce, and the Merkle tree of transactions on the network. Okay, so this is all there is from the point of view of the miner. But now a lot of weird things will happen, and we will talk about them. So, okay, one nice question here, and I really like this question in the chat, is what happens if a miner transmits this block B to someone, to some other node, and then that node tries to hijack it and send it to other people as their own block? Well, actually, that wouldn't work. Why wouldn't it work? Well, because let's come back to the block and see what kind of information it has. So this block B, of course, has the transactions, the nonce, but it also has the address of the miner. And by that, we basically mean the public key of the miner that is doing this mining, right? So if an attacker wants to steal your block, what they have to do is that they have to replace your address, your miner address, with their own. And if they do this, the nonce will no longer be valid because the hash will no longer be small. So they have to basically compute the hash again, which means that they have to do the mining of the new block again. So it wouldn't be the same block at all. So no one can steal your blocks after you announce them. Okay, so another question is, can they change the contents? No, again, they cannot change the contents, because here's the thing. So the hash of the block is the thing that has to be small. It has to be less than or equal to D, right? So if they change anything in the header, the hash will change and it will very likely not be small anymore. And if they change any of the transactions, then as we talked in the lecture on Merkle trees, the Merkle root will change. And if the Merkle root changes, again, the hash of the whole block will change. So they cannot really make any changes to your block. When you create a valid block and you broadcast it on the network, other nodes cannot change it. It's just a valid block. And if they want to change it, well, they have to basically form another block, which means they have to solve the proof of work problem that you have solved again on their own. Okay. But here's the thing. What they can do is that they can just choose not to propagate your block for any reason. Maybe the other nodes don't like you, so they will just not propagate it. And the defense against this is, again, to have better connectivity. So if you have a lot of different nodes as a miner that are connected to different parts of the network, as soon as you find a block, as soon as your proof of work and trying different hashes works, you will send this block from many different places in the network. You will announce it, for example, in Hong Kong and in the US and in Europe and so on. And if not everyone is against you, if not everyone is malicious, then it will be propagated throughout the network. Okay. So another question is, does the block have signatures? Not really. So, and actually the block doesn't need to have a signature because it has the address of the miner and it has the right nonce. So even without a signature, it's pretty obvious where the block will go, who created this block, right? Okay. So another question here is, how do these block explorers work? Because the actual transactions are not included in the blockchain. Well, the way these block explorers work is that they are basically a node on the network and they hear all the transactions. And whenever a new block is announced, its header is announced and also its Merkle root is announced. They're all propagated so they can find this information on their own. Okay. Now, the next question is actually what I'm going to talk about right now. And the next question asks, can multiple miners find the answer at the same time? Well, probably not exactly at the same time, but even if they find the answers at roughly the same time, it's a problem, right? And until this point, when I was talking from the point of view of the miner, I just said that the miner keeps track of the current blockchain and also has a mempool, just like every other node. But as we talked in the previous session, the problem is that the nodes don't just keep track of a single blockchain. They keep track of a number of chains that might end up being the longest chain. So this also happens for the miners. And so let me just create a new slide here. And let's call this like some problems miners have. So the first problem a miner has, or actually, well, I'm calling them problems, but in a sense, these are also giving miners more control over the whole system. So maybe they're not exactly problems, maybe these are good problems to have. But anyway, the first problem a miner would have is which chain to extend. Okay. And of course, the problem here is that, well, the miner is keeping track of the blockchain just right like everyone else. So this is the blockchain that they have. But of course, just like everyone else, if there was ever a fork, they keep track of both sides of it. right? Until one side gets longer than the other side. And the idea is that as soon as one chain gets longer than the others, that's the consensus chain, and we will continue working only on the consensus chain. So if we have a single consensus chain, if there is a chain that is obviously so much longer than every other chain, then the miners have no problem, right? As a miner, you just know that you have to extend the longest chain. But what happens if we had a fork like this, and now we have two chains, and we don't know which one to extend? Well, the protocol says that the miners can extend each one of these. So the miner, when they create a new block B, they can choose. They can say that my previous block is this one, or they can choose and say my previous block is this one. And you see the problem, right? The problem is that this is kind of like gambling, because if I say that my previous block is this one, and I successfully mine this block, suppose that I successfully found the right nonce to add B, it might be the case that some other miner at the same time extends this block. And then it might be the case that later on this block, this chain becomes the longer chain. So if that happens, if I mine a block, and then later on some other chain that does not include my block becomes the longest chain, then as a miner, I have just wasted all of my effort, right? Because the block that I have created is no longer in the consensus chain, and that's just the same as not existing at all. So everyone will delete this block. So the answer to which chain to extend is that it's a risky choice. So as a miner, you have to choose, but of course, this choice comes with some risk. Okay, this is the first problem we had. The second problem that we have is actually coming back to this algorithmic problem here. So several sessions back, I talked about how the miners are compensated for their efforts, because computing so many hashes is going to take a lot of time, of course, and we need to be sure that there is some incentive. Otherwise, the miners will not waste their time and resources doing all these hash computations. Okay. So we have a question here that asks, can't the miner wait to see until one chain is obviously longer? Yes, but what does that mean? That means that the miner is basically turning off their equipment and not doing the mining, while other miners are trying to do the mining and extend the chains, right? And that's not a great idea. So as a miner, you have put maybe millions of dollars into buying equipment that does this hash computation for you, and you don't want to just turn them off. You want to continue mining at any given time. So most miners will just have some heuristics or maybe choose randomly. But what happens is that, again, we go back to this very same point that I had at the very beginning. As a miner, you need to have a really good connectivity to the network. Because, of course, if I have a case like this, if I have a fork, let's say, and both sides are the same lengths, both chains are the same lengths, then as a miner, I can just choose one of these randomly and try to extend it. But I have to have great connectivity to the network so that if I haven't found a block and suddenly some other miner extends this one, then as a miner, it's in my best interest to find out about this as soon as possible and then switch to this one instead of continuing to work on this chain, right? So again, this goes back to connectivity being really important. As a miner, you want to make sure that you know exactly what's happening on the network, and you want to be one of the first people to find out if a new block is announced. Okay. But going back, so what I was talking about were the rewards. We said before that the miners are paid in two ways. So one way is the block reward, and the other way is transaction fees. So as a miner, another problem you have is how to maximize your revenue. Okay, suppose that you have invested in a lot of hardware and you're also paying a lot of electricity bills to mine these blocks and compute the hashes. But the problem is, like, how do you want to maximize your revenue? And of course, your revenue is in Bitcoins now. And okay, so let me just repeat this. As a miner, your revenue comes from two sources. So one source is the block reward. So whenever you get to add a new block to the blockchain, you get a particular amount of reward, right? And we talked about this before. We said that it started with 50 Bitcoins per block, and now it's down. It's 6.25 Bitcoins per block, and it's going to get halved over and over again. And the other revenue that you have is from transaction fees. And this was, again, the idea that the difference between the sum of inputs and the sum of outputs in a transaction is considered to be a transaction fee and is paid to the miner that puts that transaction into the blockchain. So to the miner that puts that transaction into a block and then mines that block successfully. So as a miner, your revenue comes from these two sources. And of course, you want to maximize it. And again, if you go back to the Bitcoin paper, when the protocol is designed, it says nothing about this. The only thing that Bitcoin says is that, well, you have a limit on the size of your blocks, and you can put whatever transactions you want into your blocks, but your block has to be valid. You cannot have double spending. So as long as you have a block that satisfies these constraints, it will be accepted by the network. But again, the problem is that in the real world, as a miner, you have invested a lot of money and effort into this, so you want to maximize your revenue. So the first source is block reward. And how can you maximize this? Well, actually, you can't do anything about it, right? Because this block reward is basically proportional to your hash rate, right? This is proportional to your hash rate. And by hash rate, I mean the number of hashes that you can compute per second as a miner, right? So if you have, let's say, 5% of the computational power on the whole network, then on average, you will be able to mine 5% of the blocks, and you will get 5% of the total block rewards. And since it's proportional to your hash rate, there's not really much you can do here to increase your block reward. You can, of course, increase your hash rate, but that means buying even more hardware. That's an expensive thing to do. And honestly, it's not really for this course to discuss that, because we want to keep it on the computer science side of things. And how you decide how much to invest in a hardware is more of an economics problem. But the second thing that you want to maximize are the transaction fees. And here's where I said I will come back to the algorithmic problem that we had before. So this was our algorithmic problem. When forming a block, the problem was that we are given a set of transactions. These are the transactions that are not yet on the blockchain. Let's say the transactions in your mempools. And I say mempools because as a miner, you probably have several nodes on the network. And you just want to choose a subset of these transactions that, first of all, fit into your block size, and secondly, have no double spending. Okay, so this is the problem, but now I can also say that my goal is to do this whole thing such that the total transaction fees are maximized. And I write it with a different color because this is not part of the Bitcoin protocol. So the Bitcoin protocol just says that the miners have to find a block that is valid, a block of transactions that is valid. But in the real world, the miners, of course, want to maximize their revenue, so they want to maximize the amount of transaction fees that they get. Okay, so what does this mean? Well, first of all, of course, it means that as a miner, you will ignore any transaction that pays no fees. So let me just write it here, ignore no fee or low fee transactions, right? Because if someone has made a transaction and they're not paying you any rewards, or if they're paying you a very low reward, it doesn't make sense to put it into your block because the block space is limited and it's like real estate, right? So you have limited space. You want to make sure that you make the best use of it. So if a transaction is not paying enough, you just ignore it. And this has a huge consequence on normal members of society who are making transactions on Bitcoin or on any cryptocurrency. This basically means that whenever you do a transaction, in order to make sure that your transaction will be put into a block, you have to pay a good fee. And actually, there is some sort of unwritten rules for miners to choose what kind of fees are acceptable and what fees are not acceptable. So you can just Google it. And there are different rules, but it's a free market. And in the end, you can create your transaction with any amount of fee that you like. And if your fee is low, the transaction will not end up on the blockchain. But this is just an obvious side effect. But what I was trying to talk about was the whole problem of maximizing the transaction fees. So we can think about it as an optimization problem. We can say we want to maximize the transaction fees given a bunch of transactions. And unfortunately, what happens here is that this problem, the problem of maximizing transaction fees, is NP-hard. Okay. And actually, for those of you who are interested in this, I have a paper exactly about this, and I show that not only it is NP-hard, it is also hard to approximate within a constant factor. So what does this mean? This means that, well, as a miner, you have to also find a way of trying to maximize your transaction fees, but you know that it's impossible to do it exactly. So you might use some machine learning ideas, you might use some heuristics to choose the transaction fees, but it's just a really hard problem that is left to the miners. And this problem also gives the miners some control over the network. Because, yeah, while you can think about it as maximizing transaction fees, the miners might have some other ideas in mind as well. Suppose that I am a miner and for some reason I don't like a particular transaction. Maybe I want to avoid mining transactions by a particular person or a particular, let's say, public key. What I can do is that I can say whenever I see transactions that are from this public key or to this public key, I will just not put those transactions into my block. Now, does that mean that those transactions will never happen? No, because some other miner might put those transactions into their block and mine it. But it does mean that if a miner wants to avoid mining some transactions, there might be delays in them, or the probability that they get on the blockchain decreases. So there are all sorts of attacks that the miners can do. And we will talk about attacks by the miners later on in this course as well. Okay. So these are two of the problems that the miners have. And of course, the other problem that you will have as a miner is what happens if other miners ignore you. So here's the third problem. Let me say it like this. So as a miner, you want to ensure that your block ends up in the consensus chain. Okay, what does this mean? So suppose you're a miner, and suppose that every other miner hates you for some reason. Okay, and let's say this is our blockchain right now. And let's say that as a hated miner, I create a new valid block and add it here. But since everyone else hates me, they just ignore my block and they fork the blockchain from here and continue like that. Okay, what this means is that my chain, my block will no longer be in the consensus chain because the others will be able to create a longer chain that does not include my block. And so this means that all of my effort will be lost. Now, there's really no defense against this. The only defense against this is an assumption that we have in Bitcoin. And this is an extremely important assumption, and we will talk about it many, many times. So this is the core Bitcoin security assumption. And the assumption is this. It says that a majority of the network is honest. And what do we mean by a majority? Well, remember that we don't really have a concept of people here, because every single person can create as many nodes as they want. They can create as many identities as they want. There is no limit on what they can do, right? As a single person, you can have many different computers connecting to the network in many different places, and you can create as many public keys and private keys as you like. So when we talk about majority, we have to be very specific. And generally, when we're talking about proof of work and we say majority, we mean majority of computational power. Okay. So I don't assume that a majority of miners as people are honest. What I assume is that a majority of the computational power is in the hands of honest miners who will just follow the rules and will not punish anyone or will not try to do anything crazy like this. Okay. With this assumption, I can be sure as a miner that if I add a node to the network, because a majority of the, that if I add a block to the blockchain, because the majority of the miners in terms of computational power are honest, then it is very likely that my block will end up in the longest chain. Of course, there is some limit to this. If two miners find a valid block at approximately the same time, then it might happen that the other fork gets longer, and then I lose all the energy and time that I spent to do proof of work here. But at least I can be sure that the majority of the network is not doing this on purpose. Okay. So when I add this block, if no other block is added at roughly the same time, I can be sure that other miners will continue mining after my block. and they will not fork the chain like that. Okay. So in a sense, in a sense, your security, your economic security as a miner really depends on this assumption that the majority of the network, the majority of the computational power in the network is honest. Okay. So, but what does this mean? Actually, let me just discuss something without writing it here. What does this mean for you if you're just a normal Bitcoin user, someone who's buying and selling Bitcoins or doing any kind of transactions on Bitcoins? Well, this means that you are at the mercy of the miners. If the miners decide not to let you touch your money, then you cannot. So let's say that, let me go up here. Okay, here. Let's say that you are Alice, and let's say that you have 5 units of Bitcoin. So Alice has received 5 Bitcoins here. Now, if all the miners in the network decide that Alice has done some sort of fraud, or Alice is somehow blacklisted, then they can just decide together that we will not mine any transaction that uses these 5 Bitcoins. And that's it. That means that basically Alice has lost that, right? Because if this happens, then Alice can make transactions with these 5 Bitcoins, but no one will mine those transactions. Of course, again, here is one of those points where the honesty of the majority comes into play. So again, we are assuming that a majority of the miners are honest. So we are assuming that a majority of the miners have nothing against Alice. And if they see a transaction from Alice that is using this particular coin, a majority of miners will put it into their blocks, assuming again that Alice has paid enough transaction fees and everything else is correct. Okay, but here's one point where Bitcoin and these cryptocurrencies are actually vulnerable to government control. Many of the miners are well known. Many of the biggest miners are at least well known. And what that means is that if you want to, for example, stop Alice from transacting, and let's say you are a really strong government, you can just go to the top 10 miners on the network and say, hey, from now on, you cannot mine anything that is touched by Alice. You cannot mine any transactions by Alice, otherwise I will fine you. And that will stop the miners from processing these transactions. And of course, that basically means that Alice cannot touch her money. And so what I meant by this example is to illustrate to you that this assumption, this idea that is at the very core of Bitcoin, that the majority of the computational power on the network is honest, is not actually an assumption that holds in the real world. So there are many cases in the real world when especially governments can interfere with this and make sure that this assumption does not hold. Okay? So let me just answer some questions and then I want to show you some more charts. So there's a question that asks, how long is considered to be at the same time when adding a new block? Well, there's no good answer to this. Basically, our problem is that what happens if 2 blocks are added at approximately the same time? And by that, I mean that some portion of the network sees this block first, and some other portion of the network sees this block first. So this is my definition of them happening at approximately the same time. What I mean by that is that this block is announced somewhere on the network before this block is already propagated to the whole network and the whole network agree on this. Okay. So another question here says, however, this again means that the chain is dependent on trust, something that we wanted to avoid in the system. Yes, in a sense, that's correct. So we are trusting that a majority of the computational power is in the hand of honest actors, in the hand of honest miners. But this is not exactly what we wanted to avoid. So we wanted to avoid centralization. We wanted to say that we do not trust any single person or any single entity. We don't want to have a central bank that we trust with everything. We don't want to have a government that we trust with everything. But instead, what we're doing here is a decentralized kind of trust, right? So I'm not trusting any single miner. I'm just trusting that a majority of the miners are honest. And this is kind of a weaker assumption, because you can imagine that the miners also have some incentive to be honest, because they're making money out of this system. They're, of course, getting rewards in Bitcoins. And so it's in their best interest to make sure that Bitcoin will continue to operate and that Bitcoin will not crash and burn. So it's reasonable to assume that many of them or a majority of them will be honest. And it's kind of a weaker assumption that's saying that a particular person or a particular bank is honest. So in that sense, we have trust, but we have decentralized trust, not centralized. Okay. So someone asked, does that mean miners hold a lot of power? Yes, as I just told you, if all the miners or even a majority of the miners agree that Alice should not be able to spend her money, then they can stop it. So another question is, then the more miners we have in the system, the more trustless the system is. Yes. So the best thing you can do to make Bitcoin even more trustless is to join as a miner. And basically the idea is that if we have a truly decentralized system, where, for example, let's say no miner controls more than a very tiny amount of the total hash power, of the total computational power, then this security assumption holds with very high probability and the system will be safe with very high probability. But again, unfortunately, in the real world, that's not the case. So there are a few miners, or what we call mining pools, that control a lot of the hash power. So let me show you something about that. So I have to change my screen share again and go back to the blockchain explorer. So can you see my web browser now? Great. So this was the total hash rate that we talked about. And of course, it kind of fluctuates. And actually, it also has to do with the real world price of Bitcoin. So the miners are making an economic choice. They're thinking like, how much does it cost for me in terms of electricity to mine a block? And when I mine this block, how much are my rewards worth? And most of these miners actually work in US dollars or other real world currencies. So if the cost of energy and electricity goes up, or if the price of Bitcoins goes down, then the hash rate will also go down because the miners will put less energy into mining. On the other hand, as the price of Bitcoin goes up, which it has in general, more and more miners are incentivized to put more effort into mining, and then the hash rate goes up. And as you see, so the hash rate, when it started here, it was almost zero back in 2008 and so on. And then it has grown very fast in recent years. Okay, but here's the part that is really worrying. This is how the hash rate is distributed right now. So in the same way that we could approximate what the total hash rate of the system is, of course, we can look at every particular miner and see how often does this miner succeed in adding a new block. And if you have a miner, for example, like Antpool, who adds many blocks, you can easily compute their total hash power, well, at least approximate their total hash power based on the number of blocks that they are successfully adding. Right? And doing that, we actually see that there are a few miners, actually a few mining pools. I'm not going to talk about mining pools because it's going to be in your third homework. But these are basically like consortiums of miners that are helping each other. Let's think about it like that. So think of ant pool as some sort of collaboration between different miners that are all mining together. Think of it like a corporation for now, but you will see more details in your homework. So there are a few miners, a few of these, let's say, corporations or pools that are controlling more than half of the currency, more than half of the total hash rate. So what does this mean? This means that if you're a really powerful government, what you can do is that you can just go to these mines, so 1, 2, 3, 4, 5, 6 big players, and say, hey, I have put Alice under sanctions, or this particular coin here, I don't know who it belongs to, but it was obtained using illegal activity. And you can tell all of these miners that if you touch this particular coin, I will fine you. And then none of these miners will touch that particular coin. Or you can go even one step further. As a really powerful government, you can tell all these miners that from now on, I want you to consider any transaction that touches this particular coin as invalid. And if that happens, and if these miners agree to it, which, well, there are a few of them, so it's probably not going to be too hard to make them agree, then basically what that means is that that particular person cannot touch that particular coin at all. And so governments actually have the power to freeze Bitcoin. And this is one of the most important misconceptions about Bitcoin. There is this idea that you would be able to spend your money forever and there is no control by any government on it. That's not true because of this, because we actually have some level of centralization, because in fact, it's not as decentralized as it should be. If these big players controlled only 5% of the total hash rate, that would have been fine. But since they control more than half, it's really easy to actually regulate Bitcoin. And I'm kind of surprised that many governments don't do this. And again, on this website, you can see the hash rates. You can see it, this was for the past 4 days. You can see it for the past 2 days, for the past 24 hours, and so on. And you can also see the hash rate distribution over time. Like this basically shows how much power each miner had at any given point of time. Okay. But the other thing I wanted to talk to you was about the revenues that the miners can receive. So this is the total revenues that the miners made, for example, in US dollars, based on, well, there was a currency exchange applied here, but you usually look at it in terms of Bitcoins. So this is the total transaction fee that the miners receive. And here's one curious thing. So if you look at this transaction fees in a long period of time, you see that they fluctuate a lot. And the reason that they fluctuate so much is because the price of Bitcoin is not stable. So if you want to make a transaction, and let's say that if today Bitcoin is up and it's worth a lot, I'm not going to give you any numbers because it's really unpredictable. So let's say if today the Bitcoin price is really up, then you have to pay less in your transaction fees when you're making a transaction. Because even if you pay a little bit in Bitcoins, it might be worth a lot in the real world, and then the miners might be willing to put it into their block. On the other hand, when the Bitcoin price goes down, then you have to pay more in your transaction fees. And actually, you can see a lot of other information here, right? Like total transaction fees in US dollars, fees per transaction, and all things like that. Okay. So let me stop this and go back here. So what's the final message that I want you to take home today? The final message is that the security of the network and how well it works is directly correlated with how well this assumption is realized in the real world and how decentralized the system is. So the more centralized it is, the more control the miners have, and the more likely it is that they can be corrupted and not just follow the Bitcoin protocol. But here's a particular case, and this is what people call a 51% attack. It's actually a misnomer because you don't need 51%, you just need more than 50%. So maybe it's better for me to write it as more than 50% attack. So here's the idea. Suppose that you are a miner, and let's say that you really invested heavily in hardware for doing these puzzles and computing these hashes, and you invested so much that you now have more than 50% of the overall computational power, of the overall hash rate in the network. What does that mean? That means that suppose this is the current chain. Okay. What you can do is that you can start at any point in this chain. For example, let's say I want to start here, and you can create your own fork. And then you can work on this fork. And since you have more than 50% of the total hash rate, you can make it so that your fork gets longer than the original blockchain. And as I said many times before, in the Bitcoin protocol, the longest chain is the consensus chain. So if a miner controls more than 50% of the total hash rate, they can basically control the whole blockchain, and they can rewrite the history. They can go back in time and say, okay, I didn't like what happened in this block, let's say 2 weeks ago. Okay, that's not a problem. I'll just start from the previous block and I create my own fork. And because I have more than 50% of the total hash power, eventually my fork will get longer than the current consensus chain, and then I will become the consensus fork or the consensus chain. And basically what that means is that I get to erase the transactions that I didn't like, and I get to rewrite the history of the blockchain. Okay, but now again, let me go back to this other place here. So this is called a 51% attack. And as I said before, you just need more than 50%. You don't need 51%. This actually happened, well, the attack, not the attack, but the ability to do this attack happened once in 2014. There was a particular miner or mining pool that had more than 50% of the total hash power. In that case, as far as we know, they didn't really do an attack, but they could. And the problem that we have right now is that, again, if you look at this pie chart of how the hash rate is distributed, there are these 6 miners, 1, 2, 3, 4, 5, 6, that clearly have more than 50% of the hash rate on their side. So if these 6 miners collaborate, they can rewrite the history of the whole blockchain. So what I want you to know about Bitcoin is this: there are 6 people or 6 companies that can control the history of the network, and they can change it. So do with that whatever you like, but don't trust Bitcoin more than you should. Okay, so that's the end of this session. Thank you so much, and I will stay to answer the questions in chat, but you guys can leave. Okay. So in the questions, someone said that the sudden drop in 2021 seems related to the ban of crypto mining in China. Yes, that's very likely. Okay. So another point here is that looking at this, it seems very similar to how conventional money is controlled by a few big banks. Unfortunately, yes. So again, I don't want you to be too disheartened about this because, of course, the system works and it can be decentralized, but in practice, right now, Bitcoin is very much centralized. So yes, right now, it's very similar to how conventional money is controlled. So another question is, if those pools collaborate with others, can they control the system? Yes. Basically, any number of miners who control more than 50% of the total hash can also decide that they want to rewrite the history, they want to rewrite the blockchain from some point. And right now, as I showed you, there are 6 miners that can do this if they collaborate with each other. And actually, I think even the 5 largest ones can do it. Okay. The next one says, it feels like they can freeze or sanction anyone they want by simply not mining their blocks. That's also true. Okay. Another question is how to estimate the hash rate of a miner if the proof of work problem is not with a uniform distribution. Well, I will talk about this hopefully later on, or maybe in an extra session. This goes back to the assumption that I said we will have for our hash functions, that they are puzzle friendly. So it's a consequence of the puzzle friendliness. It's not exactly uniform, but it's close enough to uniform in practice that when we're doing the analysis, we just assume it's uniform. Okay. So another good question here, a very good question here, is that, is there any point where my transaction becomes unerasable and I can be sure that the transaction is really solidified? So the rule of thumb that many people use is that they say, when my transaction gets into a block, I will wait for 6 blocks. So I will wait for 6 other blocks to come after the current block in the consensus chain. And then at that point, I say it's very unlikely that it is going to be reversed now. So most cautious people wait for 6 confirmations. You can also choose to wait for more confirmations or for fewer confirmations, but 6 seems to be an arbitrary standard that a lot of people are using. So actually, it's very likely that if you buy something using Bitcoins online, for example, if you buy a laptop using Bitcoins, you will get your confirmation in an hour. Because what they're doing is that they're waiting for the transaction to get mined and added to the blockchain, and then they're waiting for 6 confirmations, which means 6 more blocks getting added. And since each block is added at roughly 10 minutes, you will have the 6 blocks in roughly an hour time. So that's also actually a big problem with Bitcoin, and a lot of other cryptocurrencies are trying to decrease the amount of time that it takes. But generally speaking, when you use your credit card or when you use, let's say, Alipay or WeChat Pay, it's instant. But if you use Bitcoin, it's very likely that the other side wants to wait for an hour until they're completely sure that the transaction is going to be there. But of course, as the next person in the chat says, you can never be 100% sure. Because of course, again, as I just said before, if those 5 or 6 miners decide to rewrite the whole history, right now they can do it. And they can erase any transaction that you have made. So there is another question here. Oh, actually, I'm not sure if it's a question. It says, but I heard that Satoshi Nakamoto designed Bitcoin so that with the resource to attack the network, it is even more beneficial for attackers to contribute to the network. Well, that's an argument that has some merit to it. So if you have a lot of resources and if you can compute a lot of hashes, it's probably more lucrative to just be a miner and contribute. And of course, if you are one of those big 6 miners, your whole income is coming from this network and this cryptocurrency. So it's unlikely that you want to burn the cryptocurrency down and do an attack, because of course, as soon as they do an attack like this, we expect that the value of Bitcoin will plummet, right? And they will also lose their revenues. So in a sense, you can say that it's unlikely that they do these kinds of attacks. But what happens if, again, a powerful government tells the top 6 that this is how you have to do it, and you have to, for example, sanction Alice? Then, of course, they have no choice and they have to do it. And well, actually, this also gives us a very easy way of destroying Bitcoin altogether, especially if you are super rich, or again, if you are a government that really hates Bitcoin. You just have to temporarily have more than 50% of the hash power. You don't even have to buy all the equipment that is needed for that. If you can just rent it, let's say, for a while, and then you rewrite the history, then everyone will notice that, oh, Bitcoin is no longer safe. You can no longer trust it because someone rewrote the history, and then the value of Bitcoins will plummet. So that's one way of really getting rid of Bitcoin if you're a government that hates it, or if you're a really rich person who hates it. Okay. So another question is, considering the length of the current chain, isn't the cost of rewriting more than the rewards from mining? Well, it depends how long, it depends on how many blocks you want to revert, basically, right? So if you want to revert just one block, that's going to cost much less than if you want to revert 100 blocks or 1,000 blocks. But if you have more than 50% of the hash rate, again, it's possible. I'm not saying that it's a good thing to do, but it's possible. Another question is that it seems that cryptocurrency relies heavily on incentives to function properly. Yes, that's completely true. And actually, a very active field of research is game theoretic analysis of cryptocurrency protocols and also smart contracts, which we will see later on in this course. And yeah, we really rely on incentives and analysis of what rational parties will do and how games work. So we will have some of that in this course as well. So another question is, does Bitcoin get patches or updates, or has it been the same since the time that it started? Well, that's actually also something that we will probably cover. I'm not completely sure if we will have time to cover it, though. I can put a link to some YouTube videos that cover this in Canvas. But generally, there is this idea that you can patch it, but in order to make a patch, you have to make sure that more than 50% of the network, and again, when I say more than 50%, I mean by hash rate, agree with the patch. So you can change some rules, but and make some updates. For example, you can change, let's say, the size of a block. The maximum size of a block is 10 to the power of 6 bytes. Maybe you want to make your blocks larger later on. You can do that as long as almost everyone, or let's say more than 50% of the hash power, agree with it. Okay, another question is that in the case where the network wants to freeze a coin, how is the coin specified? Is it like a block having its own hash value, or the network just avoids transactions from a certain public key? Where both of these are possible. So if that coin that you want to spend belongs to a certain public key, you can say that I don't accept any transactions from this public key. And again, this is assuming that more than 50% of the network are doing this. Or you can say that I don't want to allow this particular coin to be spent. So I say this particular transaction that has this particular hash, look at this transaction and look at output number 5 of this transaction. That's a coin that is blocked and no one should be able to use it. Okay. Okay, for homework 1, exercise 1, what does the time between the steps mean? So when you design a protocol for that homework, you might want to say that Alice or Bob wait for a particular amount of time to get a response from the other side. And you have to specify how long they will wait. So do they have to wait 1 minute, 2 minutes, 10 minutes? Okay, any other questions? Great. So I'll see you in the next session. Have a great day, everyone. Bye.